Welcome to another video on the AP Chem channel, where we help you learn chemistry the easy way by showing you how to solve problems. This video is on the 2019 AP Chemistry test, and we are doing the solutions for question number 3 in the free response section. Every year after the AP test, the questions for the FRQ section are always published. So if you haven't got a copy of the questions yet, you can go to the AP Chem website and download a copy. They also actually have solutions in the what they call these answer scoring guides, and but those are short answers and sample solutions only. So I hope in the video I'll go over some of the points a little bit greater detail. So if you have the questions already, I'll let you take a look at question number 3, and if you are ready, we'll get right to the solutions. So this problem is about the compound Na2CO3. This is sodium carbonate, and it says that you have this sodium carbonate solution of an unknown concentration, and so the purpose is to try to figure out what the concentration is. The problem also says you have a 50.0 milliliter solution of that. So let me kind of draw what you expect to see in a solution with that before we start the problem. Well, clearly sodium salts are all soluble, so what you have in this case is the sodium carbonate will dissolve. So basically you will get Na plus and you will get CO3 2 minus ions. So the idea is to try to measure the concentration of this solution by using something to try to precipitate out the carbonate. And so the idea is to take the solution and add a solution of calcium nitrate to it. So when you introduce the calcium nitrate is soluble, and so it would split up into calcium 2 plus ions and NO3 minus ions. And now what happens is the calcium ion will start to form a precipitate with the CO3 2 minus, and so that will then fall out of the solution and form a precipitate. So that's really the idea, is to try to use the mass of the precipitate to then try to figure out the concentration of the sodium carbonate originally. Okay, so let's take a look at the questions. So A, we want to write down the net ionic equation for that process. So after we have sort of seen what the process is, it's fairly clear what the reaction is for this precipitation. So you have aqueous calcium 2 plus forming a precipitate with aqueous carbonate, and that will generate a precipitate which is CaCO3, and that is a solid. So that would be the net ionic equation for this precipitation reaction. Okay, so let's take a look at part B. In part B, the problem gives you a diagram which is a picture of what ions are in the solution, and in the bottom of the beaker there is obviously the precipitate that's formed, and that precipitate we now already know is CaCO3. And so we know that at the beginning we have all of these ions that we have talked about. So we certainly have Na plus remaining in the solution after the precipitate is formed, because Na plus is still soluble. We certainly have NO3 minus that is still in the solution at the end of the precipitation because that also is soluble. So because we, according to the problem, says are going to put in an excess, so this calcium solution that we're adding in is put in excess. What that means is you will put in more than you need to completely precipitate out the carbonate ions originally present in the sodium carbonate solution. So what that means is at the end you will have an excess of the calcium 2 plus that does not completely precipitate out with the CO3 minus, CO3 2 minus ions, because CO3 2 minus ion in this equation is the limiting reagent, and that limits the amount of the calcium carbonate that you are going to be forming. So what that means is in this equation, certainly there's still excess calcium 2 plus that is unused. So that should be in the picture too. So I expect that they would need to see at least one Ca2 plus ion that you would add to that picture. So then part C asks you to calculate the number of moles of the sodium carbonate in the original solution. So to just recap what we actually have, we know we have a 50.0 milliliters of sodium carbonate of an unknown concentration. We know that we've added excess CaNO3 2. And let me list some of the data that is given. So the volume of Na2CO3 solution is 50.0, as we have seen. The volume of CaNO3 2 that is added is 100.0 milliliters. And finally, you can weigh out the mass of the precipitate after you filter it out and dry it. And so mass of the calcium carbonate that is formed is 0.93 grams. And so from these numbers, you are supposed to then be able to calculate the original concentration of the unknown sodium carbonate. So let me just start right here. So to do that, you basically have to calculate the number of moles of the reaction that produces the calcium carbonate precipitate. So again, the reaction that produces the precipitate is this one. So what you need to do is to calculate the number of moles of the limiting reagent. In this case is the carbonate ion. So that definitely then comes from the mass of the calcium carbonate. So we can calculate then the number of moles of the CO3 2 minus, because in one CaCO3 there is one CO3 2 minus ion. So all you would need to do is to take the mass, 0.93 grams, and divide it by the molar mass of the calcium carbonate. And the problem tells you that is 100.1 gram per mole. And when you do that, you will come out with 0.0093 moles of carbonate. And that will all then be essentially from this source of the sodium carbonate solution. In every sodium carbonate, there is one carbonate ion. So what that also means is this is also equal to the number of moles of sodium carbonate that was originally in the solution. You can use that to calculate the molarity of the sodium carbonate, but the problem basically just asks you for the number of moles, so that is the solution, 0.0093 moles. Now part D asks, if the precipitate that was filtered out has not been dried completely, how would that affect the result of the calculation? Will the number of moles that you get for the Na2CO3 be too high or too low? So clearly, so let me write that down. If the precipitate is wet, obviously this would then contain a higher mass than the dry precipitate because it has water in it. So in this case, the mass of the CaCO3 solid that is measured is going to be too high. And you can then trace back and find out how that would have affected your calculation, because you needed the mass of the CaCO3 to calculate the number of moles. And so if the mass is too high, then the number of moles will be too high. And because of that, you use that to calculate the number of moles of the sodium carbonate. And so what that means is, at the end, the number of moles of sodium carbonate will also be too high. And finally, in order to calculate the concentration of the unknown, you have to take the number of moles and divide that by the original volume of the sodium carbonate. And so that would also be too high. So the molarity would also be too high. So the student's conjecture is incorrect. Okay, now part E asks, if you take the liquid that you get after the filtration, so the liquid is basically what is inside the beaker, minus the precipitate, the question is, will this conduct electricity? And the answer is obviously yes, because of the dissolved ions. This solution is an electrolyte, and so as a result of that, we expect that solution to be able to conduct electricity. The next part, part F, says the student then decide to use a different method to try to determine the molarity of the same unknown sodium carbonate solution. So without using this precipitation method, what you could do is to just try to take the original solution that only has sodium carbonate, which has Na plus and CO3 2 minus ions, and you can try to use a acid-base equilibrium to see if you can figure out the concentration of the carbonate. So let me write that down. So the acid-base equilibrium that we are talking about is carbonate acting as a base, grabbing a proton from H2O, turning it to OH minus, and itself becoming the conjugate acid HCO3 minus. And of course, you can write down the Kb for that. That is the OH minus concentration times the H3O minus concentration divided by the CO3 2 minus concentration. And the problem tells you this is 2.1 times 10 to the minus 4. So this certainly is a weak base. So in part 1, it says the student first tried to measure the OH concentration, and of course that would tell you something about the equilibrium because the OH concentration is right here in the equilibrium constant. So if you do not use titration, the problem tells you do not use titration. What is a way to measure the OH minus concentration? So obviously the way to do that is to measure the pH, because the pH is minus log base 10 of the H3O plus concentration. But we know the H3O plus concentration multiplied by the OH minus concentration must be equal to Kw, or 10 to the minus 14. From this equation, you see that the pH plus the pOH must be equal to 14. So once you know the pH, then you will be able to calculate the pOH, and from the pOH, then you should be able to measure the OH minus concentration. So now the next part goes back to the original idea, which is to use the OH minus concentration to try to determine the original concentration of the carbonate in this unknown solution, which is right there. So let's see how we could do that. So if you can measure the OH minus concentration, that will give you this number right there in the equilibrium expression. If you look at the reaction, you notice that the stoichiometric coefficient of both OH minus and the HCO3 minus are both 1. And they had both come from this carbonate ion. So what that means is that the number of moles of OH minus, which you can measure, and let's call that X, is also the same as the number of moles of the HCO3 minus, because they are derived with a 1-to-1 stoichiometry from every molecule of CO3 minus. Both of those are the same. And so now that we know both of those are the same, then what we can do is to use that to determine the equilibrium concentration of the CO3 minus. So let me write that equation down here so that I can give myself a little bit more room. So CO3 minus plus H2O going to OH minus plus CO3 minus. So you see in this case, I know that this is X and this is X. So whichever the original concentration of the CO3 minus, after the reaction proceeds to equilibrium, you know that this is the original concentration minus X. And that is what you can get in this expression, since you know the OH minus, which gives you both of these X, and the CO3 minus in the bottom is the original concentration minus X. And now you know that that's equal to 2.1 times 10 to the minus 4. So from that you can calculate the original concentration. So let me just write that out in one single equation so you can see. So the Kb is equal to 2.1 times 10 to the minus 4. And if you set that up correctly, that should be equal to this. And since we know X, which is the OH minus concentration, that could be measured, then you can solve for this C0. The problem doesn't ask you to actually calculate it, so that's the end of that part. So now part G asks you, in the original solution at equilibrium, is the concentration of HCO3 minus greater than, less than, or equal to the concentration of CO3 minus? So that's really talking about this solution, because we haven't added anything to precipitate out the CO3 minus. So that's the solution that they're referring to. So the question is, in this solution, after the acid-base equilibrium has gone to equilibrium, what is the concentration of CO3 minus versus the HCO3 minus concentration. So you can see that in this equilibrium, the equilibrium has a K that is rather small. So the small number right here means that this equilibrium favors the left, favors the reactant. The extent of the reaction is quite small. So what that means is when this reaction reaches equilibrium, a lot of the CO3 minus is still undissociated or unreacted. So in the equilibrium mixture, you certainly expect much more CO3 minus than you would expect the product HCO3 minus. And that is simply because this is a weak base. So I can write down the answer here. Expect more CO3 minus than HCO3 minus because Kb equals to 2.1 times 10 to the minus 4 is a weak base. So part H asks, would you expect this to be a good buffer? So this meaning that this is the solution that we are talking about. So this solution, is this a good buffer? You know that in order to make a good buffer, you need a large reserve of a weak acid plus a large reserve of its conjugate base. So in this case, what you really want for a good buffer is not just a lot of the carbonate, but you also want a solution that has a lot of the hydrogen carbonate, the HCO3 minus, at the same time. So our answer to part G already tells us that this solution is very lopsided. There's a lot of the CO3 minus, but very little HCO3 minus. So based on that, this will not be a good buffer. And I'll write down the reason too, just so you know, because a good buffer needs a large reserve of both a weak acid and a large reserve of its conjugate base. Okay, so that's it for the solutions to number 3 on the 2019 AP Chem test. We will be doing more solutions for the rest of the test. So please do subscribe to our channel. When those videos come out, you will get notified.